In week D material, we are going to solve systems of equations by first doing factorization on a matrix. So we're going to break A up into two different matrices. So it's L times U or P times L times U. So we're going to factorize it. Break A up into a product of different matrices. There are benefits to this. So for example, if we have AX equals B1, AX equals B2, AX equals B3, if we factorize A, all this doesn't change, and it's the same factorization. Factorization is faster than finding the inverse of A, just as a general note. So we can easily solve our system equations by changing our B matrix, or if our B vector changes. Okay, so fun facts. An elementary matrix is found by performing exactly one row operation on the identity matrix. There are three different kinds of elementary matrices, and I have them over here. So here I have identity. If I perform three different row operations, this is what I get. So if I swap two rows together, I get what's called a permutation matrix. So here you can see I have row 2 swapped with row 3, and it looks like identity just out of order. If I multiply a row by a constant, then the numbers along my diagonal change. We're not really going to use this one, but that's what it looks like. And then lastly, my elimination matrix. So here is an elimination step where I said row 2 equals row 2 minus 2 row 3. And we'll notice this is elimination matrix, has a extra non-zero entry. This here is my non-zero entry. It's called L. It's a multiplier. That shows up in the 2, 3 position. And notice I replace row 2 using row 3. That's where the 2 and 3 come in. Okay, so this row operation that's used it indicates how my elimination matrix is going to be constructed. And it's important to note that the inverse of my elimination matrix is the exact same, except the value on my multiplier just changes sign. The sign changes. So rather than it being -2, here it becomes +2. Okay, so why do we even care? It turns out that we can go ahead and use matrix multiplication in order to represent row operations. So if a matrix can be reduced to a strict upper triangle matrix, this being REF, using only elimination, so only row operation 3, then we can represent this reduction process in terms of matrix factorization. Or you can think about it as multiplication. That's what it means. Factorization is multiplication between two matrices. Where if I say A times E, or E times A, my bad, wrong order. Remember, order matters in matrix multiplication. E times A, if I multiply this matrix by A, it will do that row operation for me. So if I do 3 of those to reduce my to get my 3 zeros in REF, get that 0, that 0, then it's really just 3 multiplications, 3 matrix multiplications, represented like this. So E21 gets the 0 in the 2, 1 location. E31 gets the 0 in the 3, 1 location, and E32 gets the 0 in the 3, 2 location, which if you have bigger than a 3 by 3, you're going to need more, but we're going to start with a 3 by 3 and work through those examples, and then expand. The process continues for a 4 by 4. Okay. But doing my elimination steps, can be represented as 3 different matrix multiplications. So U is an upper triangle matrix. It's REF. A specific REF that's found by just using elimination that I can represent with these 3 matrix multiplications. In order to find L, where L is a lower triangle matrix, this is what L looks like. It's got 1s along the diagonals, and it's just my 3 elimination steps. My 3 elimination, I guess you can call them multipliers. The things that I used in order to multiply row 2 and row 3 by constants in order to get a number, or I guess row 1 and row 2. Okay. To find L, I just essentially solve for A. So U equals E32, E31, E21A. So then I go ahead and find the inverse of these one at a time. So E32 to get rid of that one, inverse. E31 inverse to get rid of that one. And E21 inverse to get rid of that one. So this is what ends up. A equals E21 inverse, E31 inverse, E32 inverse times U, where this is L, as you can see down here. So that means A can be broken down into L times U, where L is a upper triangle or a lower triangle matrix. So it's got ones along the diagonal, it's got values down here and zeros over here. U is an upper triangle matrix. It's got zeros down here and values over here. This is REF. And this represents how I got there. That equals A. Okay, so note it's full of the inverses. So now, how do we find L and U? Here's our process. Solve for REF only using elimination, which means we are going to use these 3 row operations every time. Every time. There's no thinking beyond this. It's memorize these 3 row operations. Do not get creative. Okay, this is your creativity. This is it. Follow these steps. Then notice we've got these multipliers here that show up. L21, L31, L32. Okay. Those would show up in the elimination matrix. We don't want the elimination matrix. We want the inverse. So we need to go ahead and change the sign. So L21 becomes negative, L31 becomes negative, L32 becomes negative. And we plug those into L, where L looks like this. L21, L31, L32, negative, negative, negative. Okay. Sometimes you might see it written as R2 equals R2 minus L21, R1. And in that case, you don't need to change the sign. Either one, just keep in mind the difference between this row operation and this row operation and how it fits into E versus how it fits into E inverse. Okay, keep that in mind. But you'll see it a couple different ways. Okay. And there we go. What we end up with REF is U. So REF is U, and this is L. That's how we do it. Another way to do it is by knowing that when we break A up into L and U, we end up with this. This is what we are aiming for. If we do the matrix multiplication between this L and this U, it looks like this. This is LU. And we can just solve for equal matrices, solve for L and U one at a time. So A11 equals U11, A12 equals U12, A13 equals U13, and then A21 equals L21 times U11, which is found there, so you can find L21 and then keep going one at a time. Okay? Okay, so that breaks A up into L times U. So now we want to go ahead and use that to solve our system of equations. Which, if we break A up into L and U, that means our AX equals B becomes LUX equals B. This is a lower triangle matrix. This is an upper triangle matrix, those are easy to solve. So we're going to break it up into 2 pieces. I'm going to extract this and say UX equals Y, which means LY equals B. What this does is it gives me 2 different systems of equations where I can solve for Y here. And I can solve for B here. Once I have Y, I can plug that in and solve for B. No, other way around. Other way around. My bad. I can solve for Y. That's why it was weird. I can solve for Y here. Once I have Y, then I can plug it in here and solve for X. There we go. X is unknown. Okay? So we just have 2 different systems of equations that are really easy to solve. This one's solved using forward substitution. So solve for Y1 first, then Y2, then Y3. So top to bottom. And then this one's solved using back substitution, just like we did with Gauss elimination. We will look at problems. Okay, that's all fine and dandy. That's all fine and dandy. But sometimes that process breaks down and does not work. Because remember, what if we had a 0 in the 1, 1 location? Then we can't do R2 equals R2 minus or plus L21 R1. I can't find a multiplier that works if I have a 0 in that location. So we need a little bit more in order to make this method a little bit more robust. And that's where row swapping comes into play. So like I said, this over here is a permutation matrix where I take identity and I just rearrange the rows, I swap them. The same thing applies. If I take P times A, it will also swap those rows. It will also swap rows 2 and 3 in A. So I can go ahead and add these permutations into my solution, into my solving process. So this process is called partial pivoting, where we use a permutation matrix. And what we're going to do is we're going to use permutation matrices to ensure that the largest magnitude entry is in the pivot location, is in the 1, 1 location, in the 2, 2 location, in the 3, 3 location, okay, in the pivot location. So this overcomes that problem having zeros where we can't use them or where we don't want them. Another thing that this does is this results in the smallest magnitude values in L, so we're going to have fractions more often. But that actually makes our process more robust and less prone to errors. Okay, but we do get an additional P matrix that's found during LU factorization where we get PA equals PLU. We've got this P here. So if we rearrange the rows over in L times U, we also rearrange them in A. Okay, so what this does is this gives us some additional steps in our solution. So we're still going to solve for REF, but we're going to do our partial pivoting first before we do our elimination steps for a given column. So step number 1 is find P1. So find which row operations, which rows you need to swap in order to put the largest magnitude, keyword magnitude, value in column 1 in location 1, 1. So just put the largest number from column 1 in the pivot location in 1, 1. Then we can go ahead and we can do our elimination steps. Find the zeros in column 1. Zeros in column 1. And then we're going to repeat in column 2. Find the largest magnitude in column 2, but note we ignore row 1 for step D because we don't want row 1 to be messed up anymore. Because row 1 is totally fine, we don't use it anymore. So in column 2, find the largest magnitude to put in the 2, 2 location, and then get your zeros in column 2. And then keep going for column 3, etc. But once again, we're going to focus on 3 by 3s. Then this gives you U. When you get to here, you get U. P can be found by taking the permutation matrix from step A and step D and multiplying them together. L is a little bit more complicated. To put L together, we just work our way back through our row operations, where we start out like this. For L32, we put negative L32 in the 3, 2 location. And then we perform the same row swaps that we did in step D. So these might change. When we do that, then we go ahead and put these multipliers, so negative L21, negative L31 in their corresponding locations. And then we go ahead and do our last set of row swapping based on step A. Okay. The difference is that this, when we get L, so I know I drew it right here as a strict lower triangle matrix, but L isn't necessarily going to be a triangle matrix. So if we want to get a triangle matrix, we have to take P times L as our final step. Okay, I'm not necessarily going to show that. I will most likely keep them separate, so not writing it as a triangle matrix. I will most likely keep L as not a triangle matrix, just in terms of solving. But just know that sometimes L, by definition, is a strict triangle matrix. But when we do PLU factorization, it doesn't show up as a triangle matrix. So in order to get into a triangle matrix, we have to do that PL. So sometimes you'll see L written as this. I will try to distinguish between the two. Okay, so how do we use this to solve systems of equations? Very similar to what we did with LU, to what we're going to do with LU factorization. But now instead of it being A equals LU, I have PA equals PLU. Because remember, if I swap the rows in LU, I have to swap the rows in A as well. Which means we get PAX equals B, There's a P here as well, because if I swap the rows in A, I have to swap the rows in B. But this gives us PLUX equals PB. Once again, a lot of people will write this as LUX equals PB, so just keep that in mind. I do tend to keep them separate. But the same thing, we're going to break this out, say UX equals Y, and then the other piece becomes PLY equals PB. We can ignore the P's where L is not a triangle matrix. Just as a note, if you don't write them separately, then you cannot ignore the P's. But we can use this to solve for Y first, and then plug it in here and solve for X. And that's how we use it to solve our systems of equations using PLU factorization.